I'm going to be talking about basically the summary of my next to most recent book that I wrote with Mark Richards, Software Architecture, the Hard Parts. The entire book is really about different ways to do trade-off analysis in software architectures. And what I'm going to summarize today is the last chapter, because we spend 15 chapters illustrating all these trade-offs, and this shows you how to actually apply those things. So what happens when there are no best practices? So I want to talk about the concept of best practice for just a moment. Because a best practice means that when you encounter a particular situation, you can just turn your brain off and always do this thing, because it is the best practice. It's not even a better practice, it's the best practice. If it were better, then you might question it, but it's the best, so there's no reason to question it. It has to be the best thing. But you can't do that in software architecture. This is why software architecture is so difficult, because it's hard to say, okay, I've solved that problem forever, which is a best practice, because so many things defy that. And you have to keep analyzing trade-offs over and over again. And I'll give you some examples of this as we go along. Now, one of the things you may think, one of the things you do as a developer is get really good at Google. In fact, I bet everyone in this room is really good. If you get a compiler error or deployment error, you know exactly what part of the stack trace to put into Google to get the best results and find out what's wrong with your system. But what happens when you try to Google architecture stuff? Like, for example, if I ask Google, should I use orchestration or choreography for my accounting workflow? Google's going to say, I don't know, it depends, because it can't know that. Well, of course, this is kind of outdated. You wouldn't use Google anymore for this. You'd use ChatGPT, right? And then AI. So let's try that. Let's ask ChatGPT for some architectural advice. So I asked ChatGPT, should my architecture for the accounting system use orchestration or choreography for my workflow? And it gave me a really nice, statistically likely, but mostly incomplete response to this, which is, of course, exactly what ChatGPT does. And notice the last line here. Ultimately, the decision to use orchestration or choreography for updating the general ledger and accounting system will depend on the specific requirements and constraints of the system. It's important to carefully consider advantages and disadvantages of each approach and choose the one that meets the needs of the system. This is ChatGPT's very long-winded way of saying you have to analyze trade-offs in software architecture. So even ChatGPT won't help you trying to figure out how to do stuff in software architecture, and won't for a while now. So, but this gets to a slight digression, and I could easily spend the whole session on this, but tools like Google and even more ChatGPT give you knowledge, but not wisdom. Knowledge is great, but you have to apply wisdom to know how to use knowledge. So it's going to be incredibly important for how do I configure Kubernetes to do something? That's knowledge. Should I use Kubernetes is wisdom. And that's what it can't tell you is should I do that, because it doesn't know how to do trade-off analysis. And of course, that's the key in software architecture, is doing this kind of trade-off analysis. Now, one of the things that Mark and I wanted to do in our Hard Parts book, a book purely about software architecture gets to be kind of abstract. And when we wrote our Hard Parts book, we realized that it could either be a 200-page book, a 25,000-page book, or a 450-page book. If it were a 200-page book, it would be all these abstract concepts in software architecture with no grounding, and nobody would want to read it. If we followed every possible trade-off to its logical conclusion, it would be a 25,000-page book, and nobody would read it because it's way too long. And what we settled on was a 450-page book where we talk about the abstract ideas in architecture, but then we have an example called the SysOps Squad where we illustrate how all these trade-offs come about. And we'll see some examples taken from the SysOps Squad a little bit later on in this talk. One of the things that's hard in software architecture, like distributed architectures, is service granularity. What is the appropriate level of granularity for a service in my microservice architecture? And we spent an entire chapter talking about this, which I'm going to summarize today, My talk summarizes this. I'm doing a talk tomorrow that digs more deeply into this, and my co-author Mark is also doing a talk that digs more deeply into this concept. But this is really tricky because, well, the answer to this is easy. It's supposed to be a single responsibility principle. Okay, that's great, but are all messages, notifications, a single responsibility? Are all customer notifications a single responsibility? Or is each kind of customer notification a single responsibility? So now you can have these marvelous philosophical discussions amongst software architects about how singular is single in this world. Well, this is not very good advice. So what you need are tools. One of the things that we really highlight in our book is this idea of iterative design in architecture. I don't know any architect that's so smart that they can just look at a complex problem and the solution just falls out of their head into a diagramming tool or whiteboard or something like that. What you need to be able to do is to create a candidate architecture and then iterate on that design to refine it and make it better. But to be able to do that, you need tools. You need techniques that allow you to iterate on your design. And so what Mark and I did in the Hard Parts book was come up with two different forces in distributed architectures, things that we call disintegrators. These are tools that you can apply to say, I should consider breaking my service further and further down, but they're also integrators, which I'll talk about in just a second. So here are some of the disintegrators we talk about. And the first one is the obvious one, service functionality. What function does this thing serve? This is the classic single responsibility, keep it down to basically exactly what it does. But the problem you run into if you only apply service functionality, let me go back one here. If you only apply service functionality is that you end up with lots of really teeny tiny microservices, almost down to the method level. And then you discovered you've created the slowest microservice architecture ever. Because now, instead of method calls, you're making network hops, and that's really slow. And so a common problem in a lot of, especially early microservice projects, is our services are way too small, and that's causing performance problems and transactional problems and all sorts of other things. So if you only follow service functionality, you end up in sort of an unfortunate place. The next one of these is code volatility. Now, one of the things that happens in the software architecture world are these little cults that grow up around techniques, and one of those techniques is volatility-based decomposition. And you'll talk to some architects that say that's the only thing you should ever look at is volatility-based decomposition. You know that's bad advice because it says either the word always or never in conjunction with software architecture, and that's never true in software architecture. It turns out that people who really like volatility-based decomposition, it happens that they work in a place that has to do a lot of volatility-based decomposition. There's a clear line between those things. But this is basically looking at how fast does code change. Because, and this is a common mistake that a lot of people make about reuse, is it's difficult to reuse volatile things. Because if it changes a lot, trying to reuse it means you're constantly having to change to reuse that thing. And so this is actually a good measure if something should be a candidate for reuse, or should I not try to use this because it's changing so fast. But this is another great disintegrator. Hey, I could look at volatility and break this down depending on the rate of change between these two things. And notice, this is not even really an architectural measure, this is a version control measure, but this tells you about the activity around that code and what you might want to do to it. The third one of these we call scalability and throughput, but this is really kind of a placeholder for this whole family of architecture characteristics that we call the operational architecture characteristics. Scalability, throughput, elasticity, performance, all these things in architecture that overlap with operational concerns. And this is obviously one of the places where if you have one part of your system that needs to be really highly scalable, you may want to break that apart from the other parts of your system that don't need high scalability. This is, of course, one of the advantages of a distributed architecture like microservices versus a monolith, because if you're in a monolith and you want to make it more scalable, you have to scale the entire thing. which is difficult in many cases. Whereas in microservices, because you have bounded context, well-established service boundaries, each service can have its own set of architecture characteristics. One service may be much more scalable than another. One may have much higher security than another, and it gives you more options. And it allows you to write simpler services, because I don't have to write one thing that is massively scalable and performant and high security and all these other things. I can isolate those at the service level. The third one of these is fault tolerance, which is kind of a special case of operational architecture characteristics, but this is around reliability, availability, and those kinds of issues that you run into often in distributed architectures. And then the last of these is security. And this is also another obvious disintegrator. If one part of my system needs to be much more secure than another part, it's hard to make the entire system secure, but if you can isolate that to a smaller area, then it's much easier to be able to do that. These are 5 generic disintegrators. And in general, generic advice in architecture is difficult, because it's hard to make generalized statements around something that changes so much like software architecture. And so we emphasize that this is just the starter set. So part of your job as an architect is to carry a toolbox around with you. And over time, you want to add tools to that toolbox that allows you to become a better architect. Here are 5 tools that I've now given you that you can put in your toolbox when you're doing microservices or distributed architectures as a way of iterating on that design. But I want to emphasize the fact this is never going to be a complete list, because you and your organization will have its own disintegrators that you need to pick up and put in your toolbox. It's one thing to become really good at generic architecture, but it's not that useful for you, because what you really need to do as an architect is get really good at your architecture. It doesn't matter what you know about the general principles of microservices. You need to be able to apply that to your ecosystem. So you should be actively looking for more disintegrators that work within your organization. Maybe it has to do with geography and the way developers are placed. Lots of other factors may play into building your own set of disintegrators. But very often, particularly when you are taking a monolith and restructuring it, disintegrators are all you use. But that's also a mistake, because the opposite of disintegrators are integrators. These are forces that encourage you to bundle things back together when you've broken them down too small. And there are 3 generic integrators that we talk about. And the first big one is transactionality in database transactions. As you know, in microservice and distributed architectures, you should try as much as you can to avoid doing distributed transactions, because it's the hardest problem to solve. That's actually a climax of our book, Software Architecture, the Hard Parts, is how to analyze transactionality in distributed workflows. And I go into a deeper dive on this topic tomorrow in my granularity and communications talk in distributed architectures. If you can avoid doing transactions, you should. And this is a force, because if you find yourself, I really need to do transactions between these 2 services, you can fix that by bundling them back together into a single service. And now you're within the service boundary, and now you don't have to worry about distributed transactions. That's an integrator. I've broken things down too small, I need to merge them back together. Data dependencies is another big one in microservices. You know, it's pretty easy to go look at code. We have refactoring IDEs and break things apart and shuffle them around and all that. But then you have data dependencies. And it's way harder to break these things down, because you have foreign key relationships, referential integrity, and stored procedures and views and all those things. And if you find yourself, well, I'm breaking all this data down and now I can't get it all to work, maybe you should bundle those back together and see if that solved the problem of data dependencies, so you don't have to do inter-service communication or data replication or solve a problem like that. And then finally, workflow and choreography. Should you use orchestration or choreography for your workflow? Well, it turns out that the complexity of your workflow doesn't change if you pick orchestration or choreography. It just moves the complexity around. And for really complex workflows, it's really nice to have an orchestrator to manage state and exceptional conditions, error handling, because if you don't have that, all that code has to be spread out amongst your choreographed components. And if you find yourself with these really complicated workflows, you may consider, well, what if I just bundled all these things back into a single service and all those workflow concerns go away? But hopefully now you can see what I'm talking about here, that you create a candidate architecture and then you start disintegrating it. And you get too small, and now you iterate on it and integrate it back together, and then look to see, do any of the disintegrators apply again? This is iterative design in software architecture. You don't have to be a genius and a savant to be able to do architecture. You need tools to allow you to iterate, and that's exactly what these tools are, that allow you to come up with the best, Mark and I very famously say, that in software architecture, you're usually not looking for the best design, because the best design implies that there are no trade-offs and everything is perfect. Instead, what you're looking for in software architecture is the least worst design. What's the least worst combination of these forces that will allow me to be successful, because it's hard to make everything exactly perfect in these kind of architectures. One of the things you have to think about in distributed architectures that we talk about in chapter 6 of our book is pulling apart operational data. And there are a lot of forces that encourage you to break apart operational data. And these are database granularity drivers. And part of these have to do with the scope of architecture characteristics, what we refer to as an architectural quantum. Change control. If you talk to a single relational database and it changes, everything that talks to it has to change. That's a coupling point. And so that may encourage you to break that database apart so that you limit the scope of schema changes so that it doesn't ripple out across your entire architecture. Number of database connections is another one of these database granularity drivers to encourage you to break things down, because distributed applications, it's sometimes too easy to swamp a single database because you have so many connections going into it. Everybody here is having trouble with the clicker because there's some kind of Bluetooth interference or something in here, because mine's not even infrared, it's Bluetooth. So scalability is another one of those problems. I may not be able to scale my database sufficiently to manage the number of requests I have. There's a sort of a built-in limitation in monolithic architectures, because the monolith can't get so big that it can swamp a database, but distributed systems absolutely can get so big they can swamp a database. And then finally, fault tolerance. If you have a single database and it goes down, you're done. There's nothing else left you can do, and breaking that apart into separate pieces is a good way to mitigate that problem. So let's talk about some of the trade-off techniques that we cover in the last chapter of our book in how to analyze trade-offs. And here's the first one. Watch out for the out-of-context trap when you're analyzing trade-offs. Not surprisingly, we spend a lot of time in our book building matrices to compare things. And so let's look at a common problem that you might encounter. There's a serious issue. This is not even their clicker. This is my clicker that's not infrared, it's Bluetooth. So there's some crazy Bluetooth stuff going on in here somewhere. I can't decide whether to use a shared service or shared library for the common functionality in this system. In other words, should I use, this may be chancy here, that'll never work. Should I use a compile time bound shared library, compile it into each of my services, or should I make an inter-service call and call those things? Sounds like an interesting question. There is no obvious answer here, so I need to do trade-off analysis to help me figure that out. So you build a matrix, and you try to figure out what are the pertinent facts that I need to evaluate here. The first of these is, do I have heterogeneous code or not? In other words, is everything in the same platform or some things in one platform and some in the other? Because a custom shared library is really hard if you have heterogeneous code, because now you have to build multiple versions of that shared library for each platform or technology stack and then keep them in sync or version them, or that's a headache. Whereas a shared service is great. Now you're just making a network call and it doesn't matter what that things and each of those things are written in. So in this case, a shared service is definitely a better way to go. High code volatility is much better if you use a shared library, because if it changes a lot, then you get compile time bound and you find out if it breaks something right at compile time, right at build time. Whereas if you have high code volatility, then you don't have to change it over and over and recompile all your services. As soon as it changes in the shared service, people that call it automatically get the new version of it, and you don't have to worry about rebuilding things constantly and the churn of having to update things on a constant basis. The ability to version changes is easier in the shared library, because versioning in a distributed architecture is a headache. It's possible, but it's much more difficult than managing versioning at the shared library level. So custom shared library wins in that case. Dependency management. I have clear-cut dependencies for my shared service, and that's going to become a headache, whereas I don't have to worry about that so much for my shared service approach. Overall change risk is really nice if you use a custom shared library, and it's more risky if you use a shared service, because what if that thing changes at some point over time and now you don't find out until you actually call it? You get a much earlier notification of change as you try to compile that into your system. Performance is going to be much better in a bound in-process custom library than another network hop. And so that may be a concern. Same for fault tolerance. Once I've bound it into that component, then I know it's going to work, whereas if I'm making a network call, there's always a chance that shared service is going to be down or not available, and then I have fragility in my architecture. And then finally, scalability. Which one of these is going to be more scalable? Clearly, the custom shared library is more scalable. Wow. Clearly, the custom shared library is going to be more scalable because it's in process, doesn't have to do network calls, etc. So, looks like custom shared library is the winner. This is the out of context trap. Because when you build a matrix like this to evaluate trade-offs, you sort of assume that they all have equal weight and value, but that might not be true. It turns out that, hey, we leverage polyglot programming here, and we have services written in 4 different languages in our application ecosystem. Performance and fault tolerance aren't big concerns for us. It's all about managing change to shared functionality. Oh, with this extra detail, that means that it's going to be really hard for you to build a custom shared library. I have to write 4 of them. And I have to manage the change, etc. And so the point of the out of context trap is all of these things don't have equal weight. Some of them are going to be more weighty than others, and you need to prioritize these things by what is going to have the most impact or make the decision for you. And in this case, because we're in a polyglot ecosystem, a custom shared service, even with its few disadvantages, is much easier to deal with than the equivalent disadvantages for the shared library. So turns out, after all, the shared service is the winner here. Here's the next pro tip. Model relevant business use case scenarios to extract what trade-offs you need. So here's the scenario. I wonder if we should have a single payment service or separate service for each payment type. This goes back to the single responsibility thing again. Are all payments a single responsibility, or is each kind of payment a single responsibility? Good question, and irrelevant to actually building something. It's a nice philosophical discussion, but doesn't get you anywhere. So here are the 2 scenarios. I have a payment service that manages credit cards and PayPal and sending gift cards, etc., or have 3 individual services? Which is best? We don't know. One of the problems in software architecture is that sometimes you're building something that has literally never been built on planet Earth before. The forces that you are working on are a unique combination of things, and maybe nobody's ever solved that problem. So in that case, Google nor ChatGPT are going to be able to help you with that. So how do you make this decision? Do you just put up a dartboard in your office and throw a dart and say, hey, look, the dart hit that one, that must be it? Well, you model relevant business use cases. This gets you back to the context of the solution that you're trying to make. So let's look at some examples of this. So I have a single service or shared payment services. So let's look at one scenario that we do all the time, update credit card processing. Maybe I need to change the way that credit cards work in my ecosystem. In the single service, now I need to make a change to the code around credit cards, and I need to make a change to the database, and I'm going to have to retest the entire service because I'm fiddling around with the database schema, I'm changing some code, I might have broken one of the other services, so now my scope of testing is going to be a lot higher. Versus over here in the individual services, nice, clean isolation. I only touch one of them. It has its own data and its bounded context, its code. The other 2 services don't even care that I've updated that one. So that's pretty nice. So for update credit card processing, I get separate maintainability, testability, and deployability if I use individual services. But one of the observations that Mark and I made in our Fundamentals of Software Architecture book, the one that came before the Hard Parts book, was our first law of software architecture. So as we were writing that book, we were trying to find things that seemed universally true in software architecture. And we were hoping there were going to be like 10 or 12 of these things. And it turned out there were really only 2 that were universally applicable. And the first one is directly related here. Everything in software architecture is a trade-off. But there's a corollary to that law that says, if you think you found something that doesn't have trade-offs in software architecture, it just means you haven't found the trade-offs yet. Keep looking, because everything in software architecture, it turns out, has a trade-off. And so that means we should do another use case scenario here. So let's see what the next use case is. So add a new payment type. What if we wanted to add a new payment type to our ecosystem like gift cards or something like that? So in the shared service, I add a reward points. Well, we already have gift cards. We add reward points. Now I've got to add new code to my shared service, and now I've got to update the database schema. And again, now I'm testing everything to make sure I haven't broken something in that service. Versus the individual services, I just add a new service. I'm done. Don't have to touch any of the others, don't have to fiddle with those at all. So that looks really nice. And so adding a new payment type, it turns out the individual services give you really nice extensibility. But we still haven't found a trade-off. So let's try another one. Use multiple types for payment, which is also something that we commonly do in our organization. Easy in the shared service, because they're all there. So I can easily put several payments together. It's one record in the database, one transaction in the database. Really nice, simple to do that. Over here in my individual services, now I've got transactionality problems, because what happens if you want to pay part with a credit card, part with a rewards card, now the 2 separate databases have to be updated individually, but we need to make sure that's an atomic transaction. Now I'm trying to do transactions at the architecture level, which we've already said is kind of a bad idea. And so this one's much more complicated in that scenario, because I need data integrity and synchronization across all the data in this ecosystem. So separate ones give me performance and data consistency headaches here. This is a great example of iterating through your design until you find the forces that really drive you in one direction or the other. Because now You can do the trade-off analysis. Which is more important for my ecosystem? Is performance and data consistency more important, or is extensibility and agility more important? Here's why this exercise is so useful, because when you go to your boss who wants you to build a payment service, and you start telling them all these details about microservices and transactions, and you'll quickly see their eyes kind of glaze over and they'll just go to their happy place because they don't care about all these details. Part of your job as the architect is to go through all the technical details and then roll it up into a nice, concise summary. Because you have to tell your business, look, you can't have everything. It would be awesome if we could give you a perfect solution with no trade-offs, but that doesn't exist. So now you get to prioritize what's more important to you as a business. Is it performance and data consistency, or is it extensibility and agility? Now your business is going to come back and say, well, I want all of it, of course, but you can't have it. It'd be nice if you could, but you can't. Just because you really, really want something doesn't mean that it's going to come to pass. And this is a good way as an architect to illustrate to the business exactly what forces are at play and let them make the relevant business decision of which is really more important to us as an organization. The next pro tip, compare like things. We're constantly asked to compare things in software architecture, but you have to make sure you're comparing two things that are in fact the same thing. There's a concept that comes from the strategic design patterns world called a MECE list. A MECE list is a list of things that are mutually exclusive and collectively exhaustive. In other words, if I'm looking at a problem space, I want solutions that cover the entire problem space with no overlaps. Because if I have no overlaps, then I can choose one versus the other. Of course, the overlaps mean I can't really make a distinction between those things. And you want to make sure that it covers the entire problem space and doesn't have big giant gaps. That's mutually exclusive. They're separate from one another, but collectively exhaustive, meaning it covers all the things that I need to be able to create the solution. So, no overlaps and cover the entire space. Here's a great example. Should we use a message queue or an enterprise service bus for messaging in my ecosystem? Well, this is an invalid comparison because these things are not mutually exclusive and it's not collectively exhaustive. Because an enterprise service bus includes mechanisms like a message queue, but the message queue doesn't have all the stuff an enterprise service bus has. And so now what you need to do is actually put together two things that are like one another. And so I need to add to my left a choreography engine and integration hub along with messaging, and now I have two things that are more or less similar to one another. And now you can start asking the question, should I use three a la carte things to solve that problem, or is one thing a better solution to that problem? Does it do all the things I need to do? This is getting us back to an apples to apples comparison in software architecture. It's really important that you make sure you compare things in a valid way, and MECE list is a way to get you to that. Here's another example. Don't over-evangelize any particular technology or solution. You find a lot of architects who get really enthusiastic about stuff because we're all technologists and we love to find new shiny things. In fact, a lot of the reason you're here at this conference today is to find new shiny things you can go play with back at your office and back where you're working. And it's easy to become evangelists for the new shiny things that you discover. But it's a dangerous trap because that evangelization will eventually run into a brick wall at some point. And let me give you an example of that. A software architect says, I always use publish and subscribe broadcast messaging using topics because it's the best at supporting architectural extensibility. What do you mean by that? So if I use individual queues for a workflow like this, then I've got all these headaches I have to deal with. I have And if I want to add a new one, even more headaches. I have to worry about what contract goes to each of these. I have separate infrastructure for each one of these, a separate queue. If I want to add a new one, I have to add another queue, which means I have to add my bid history. I have to add another queue. I have to change my producer. I have to build a new contract to be able to send to it. So a lot of changes have to happen if I model these things on individual queues. Whereas, if I use a topic, a lot of those problems seem to go away because now I just add bid history and have it listen to the same topic all the others are listening to. Done. This is why I'll always use topics, because it gives me better extensibility at the architecture level, and I'm going to evangelize this solution all over my organization because this is clearly the way to go. Because single producer, single contract, don't have to change anything. That's beautiful. What about data security? It turns out everybody has access to the same information in that topic. Data PII information, one of the things you have to watch out for, particularly in regulated environments like GDPR and increasingly in more and more countries. We have health insurance considerations in the US around HIPAA. What if by putting all that stuff on a topic, you end up exposing information that one of these services could put together and find out something they shouldn't be able to find? Ooh, that's kind of a problem. What if we need separate contracts for each of the subscribers? Because I'm sending everybody the same contract. Now, what a lot of the evangelists for topics would do is just say, well, let's just add all the stuff you need for all the services into that one contract. But now you are creating a problem called stamp coupling in software architecture. You're sending more than you need to, and that means that if the first bid capture here, if you change something in that contract that bid capture doesn't care about, you still have to update bid capture because you're sending the entire data to it every time, and it gets big and it gets ugly. That's what's called stamp coupling, which is an anti-pattern in software architecture. And it also makes your architecture more brittle because now if I change the contract on behalf of bid history, I now have to go change the contract for bid capture too because they're only using one contract. One of the things to avoid in software architecture is brittleness. And we define brittleness as when something changes that this other thing doesn't care about, you still have to change this too. That's brittleness, and you should try to avoid that as much as possible because it's going to drive a lot of churn in your architecture. And finally, how are we going to monitor the queue depth and use auto-scaling for the services? Oh yeah, how can I find out how much traffic is actually going through this thing? Because I don't have individual queues. I can't use auto-scaling for my queues in that case. So if one of these has a lot more traffic than the others, that's going to end up getting drowned in that single topic. And so now this gives you the chance to actually do a trade-off analysis. Queues for point-to-point messaging are published and subscribed using topics. So for queues, you have heterogeneous contracts. Each service can have its own contract, which might be nice. You don't have to overspecify that contract. Security access and control of data is much better if you use individual queues because you know exactly who is sending information to who else, which is nice. And you get operational facilities like queue monitoring and auto-scaling and a bunch of other things that are really nice, particularly as your architecture scales and grows. But using topics is really nice if you need extensibility. You need to add more customers easily, which is the main advantage of using a topic. So now, which is more important? Because again, neither one of these is a best practice. You have to do trade-off analysis. Now you can go to the business and say, okay, business person, decision maker in my organization, which is more important? Data security and separate contracts, or is extensibility and agility more important? Because you can't really have both, and so now let's prioritize these things based on the domain and the problem that we're trying to solve. See the problem of trying to evangelize generic solutions in software architecture? You always bump into boundary conditions and error cases where you can't really do that. and now you need to do actual trade-off analysis. Here's the next one. Don't overwhelm your business stakeholders with too many trade-off choices. Bottom line them instead, which is largely what I've been doing throughout this talk. So here's an example of that. I can't decide if we should use synchronous or asynchronous communication to kick off the credit approval process after accepting the application from the customer. Common kind of trade-off to deal with in a distributed architecture like this. So let's see what the relevant cases are here. So one thing I could do, I have my service here that needs to call and collaborate with these other services. So the communication from here to there is what I'm curious about. So if I use a synchronous connection to do that, something like REST, for example, I make a call to it, and now it's going to go through all the process. I'm waiting, I'm blocking and waiting because it's a synchronous call. That entire credit approval process will have started, and then it'll send me a response back saying, okay, we've started your credit approval process. So you know that things have gotten started, but the consumer is having to wait for a while for all this workflow to work its way through the ecosystem. Versus asynchronous, I can fire and forget. Post to the message queue, get acknowledgement, it's on the message queue, and now my credit approval application service can go off and do some other stuff, handle some other requests, etc. But then I have to build a mechanism to notify me if something went wrong so that I can take some response to that, because I've lost that request response cycle that you have in synchronous communication. Going to your business people, your domain experts, and trying to explain this to them is sort of like a plumber coming to your house and saying, you really need to replace all the pipes in your house because there's this brand new material called unobtainium that's the best possible characteristics of water pressure and mineral content and all these details. And as a homeowner, it's like, I don't care about all this stuff about plumbing. I just need water to show up when I turn on my tap. So don't drown me in all these details. Is the water working now? Then okay, I don't really need all that stuff. And that's what the business says when you come to them and start droning on about all these architecture concerns. And so you should bottom line it for them and put it in their terms. If I use synchronous communication, the customer is going to have to wait for the credit approval process to start, which has an impact on responsiveness. And this may be a little while, several seconds, for this entire workflow to come back to me, but the credit approval is guaranteed to start before the customer request ends. I get that nice request response handshake, so yes, I know that this thing has actually started when things begin, but the customer application is rejected if the orchestrator is unavailable. If I try to make that synchronous call, that orchestrator is not there, then I'm going to get error conditions. Versus, customer doesn't have to wait for the process to start. That's really good responsiveness. But no guarantee from the customer standpoint that that credit approval process has actually started, because I've lost that request reply kind of thing. But on the flip side, the application process is not dependent on the orchestrator availability. One of the nice things about message queues is I can post a message to a queue, and then it can, if that orchestrator is down, it can just hold it there until the orchestrator comes back up and then complete that workflow. And so I have more resilience to temporary outages and other sorts of headaches like that. So now you can go back to the business and say, okay, then which is more important? Do you want to guarantee that the credit approval process is actually started, or is responsiveness and fault tolerance more important for this architecture? It's important for architects to learn how to speak in the language of the business, because the business is never going to learn to speak your language. You are the bridge between the technical solutions that the developers are going to create and what the business people really need. And it's really convenient for them if you can take all these details and wrap them up into a few simple decisions that they can make, this trade-off versus other trade-off. That is the essence of trade-off analysis in software architecture. And then finally, a technique that we used a lot in our book is to use qualitative analysis to iterate on design, leading to quantitative analysis. As I alluded to before, a lot of times in software architecture, you're building something that's never been built before, which means you can't measure it. That's quantitative analysis. So what you do in the early stages of design often is qualitative analysis. So let's talk about the difference between those two things. Qualitative is relating to measuring or measured by the quality of something rather than its quantity. Quantitative is the opposite. It's measuring the quantity of something. It is a direct measurement for something. And let me show you where that is pertinent. And this is a topic that I go to in excruciating detail tomorrow in my communication talk. As I mentioned, the sort of finale of our hard parts book is how to manage transactional sagas. And it turns out that one of the observations that Mark and I made is that there are what we call three primal forces you have to think about with transactionality in distributed systems. And those primal forces are communication. Is it synchronous or asynchronous? Consistency. Is it atomic or eventual? And coordination. Are we using choreography or orchestration? When Mark and I were writing the book, we wanted to say some interesting things about transactional sagas, and then we kept building all these workflows, and then we'd build one, and then we'd say, okay, well, what happens if you change coordination from orchestration to choreography? But then it shuffles all the numbers. Everything changes. You've made one small change, and now everything is disrupted. And at one point, we realized why that is. This is a three-dimensional conjoined space. You can't make any one of these decisions independently of the other two because they all are tangled up and affect one another. This is where the terrible advice comes in software architecture. Always use asynchronous communication in distributed architectures. Well, there are two problems there. One is the use of the word always when talking about software architecture, which is never a good idea. And the other is trying to default to something as important as this, because it turns out it can drive the complexity sky high sometimes if you have the right combination of forces that you're trying to model here. And so here's an example of qualitative analysis. So Mark and I looked at this problem and then realized if you treat each of these three forces as a binary, what you have are 2 to the third power possible combinations, which is 8 combinations. So let's model all 8 of them and see what happens. Now, all of these are sagas of one kind or another. A transactional workflow in microservices is called a saga, and so we named all of these kind of whimsical names for kinds of stories and basically changed each value one at a time to see what impact that would have. And it ended up with 8 different variations of this saga. And we thought, going through this process, that if we model all 8 of these, probably 4 or 5 of them will just fall away as being ridiculous and not realistic, and then we can do a deep analysis on the others. Turns out all of these are either legitimate patterns or anti-patterns that you see out in the wild all the time. We were really shocked at how common a lot of these things were in the wild, and they're all about these 3 forces: communication, consistency, and coordination. This 3-dimensional conjoined space, you always have to take all 3 of those into account every single time. And that led us to these 3 different forces and this summary of those for our sagas. What this allowed us to do is qualitative analysis for these different sagas. Because I don't know for sure what the exact numbers are going to be, but if I look at synchronous to asynchronous, I know asynchronous is going to be more scalable. So I can give more weight to scalability for asynchronous communication than for synchronous communication. Now, in a perfect world, When you encountered a problem in software architecture, you would go and just build it in all 8 different variations, measure each one of them, and then pick the one that's the winner. So now you get to go to your boss and say, hey, you know that workflow we're working on? It's going to take me 8 times longer to build it than you thought it would, but it's going to be perfect when I'm done. I know we'll have the best solution. That's going to be a tricky conversation because they don't want you to take 8 times longer to build it. They'd like you to build it quicker. And so this is where qualitative analysis comes in. The quality of these things you can judge in a generic way against each other and narrow it down to just 1 or 2 and actually implement those and go to quantitative analysis. Now make no mistake, you want to get to quantitative analysis and actual measurements of things with metrics and other sorts of real facts, but a lot of times you can't do that in the early stages of design. And there's a real value of going through the exercise of looking at each one of those from a qualitative standpoint, because what this allows you to do is rate them against each other. And this is exactly what Mark and I did on our book. We have dots. 2 dots is the most you can have, and we have red, yellow, and green dots. And here are all the different saga types, and these 4 characteristics where they differ the most: coupling, complexity, responsiveness, and scalability. They differ in a lot of other ways, but these are the ways that they were most obviously different from one another. And so this allows you to make some judgments at the software architecture level, because you may have heard some advice from somebody that says, you really shouldn't use orchestration in microservices because it drives up complexity. And sure enough, look, the Epic saga here uses orchestration, and it has a lot of really bad complexity in it. But now I have an analysis. So I can say, well, but is orchestration really the culprit here? Because I can go over here to the parallel saga, which also uses orchestration, but it has much better characteristics. It turns out it's the deadly combination of atomic and orchestrated that's driving all the bad behavior here. Again, you can't treat any one of these things as a single thing. It's the conjoined force of all 3 of them. And doing this qualitative analysis allows you to sift those things out so that I can make some judgment calls here to say, well, what is really important to me? Is it consistency? Is it communication? Is it scalability? If it's scalability, I'm going to look along this chart for the things that are most scalable, and then maybe complexity is the next one. So, well, the anthology saga has fantastic scalability, but it's kind of high in complexity. Maybe I should use the time travel, which gives me a green dot on both of them. So this gives you a way to analyze this problem before you've actually built it by doing qualitative analysis, and then we encourage you to actually build it and measure it to make sure that things work the way you think they do. So some observations about doing this kind of qualitative versus quantitative analysis. There are 3 coupling drivers that we see here: atomic, synchronous, and orchestration. Those are the things that drive coupling up higher. There's a direct correlation between the complexity of your workflow and how useful an orchestrator is. One of the observations we made in our book is that every workflow has what we call semantic complexity in it. If you're placing an order to book and it needs to go to order fulfillment and then send notification, that is the semantic complexity. But then there's also implementation complexity. And the point is, no implementation will make semantic coupling less, but it can make it a lot worse. And so if you have a really complex workflow with a lot of boundary conditions and error possibilities, having an orchestrator is really nice because it gives you a place to manage those things in one place. Versus if you're using choreography, you have to split all those semantics across all those domain services, which now they need to know more about each other. In orchestrated services, the domain services can be happy and dumb. They don't have to know they're in a workflow. Somebody's telling them what they want and get it back. In choreography, they have to know about each other. They have to know what happened in case of an error. And if in choreography they're involved in more than one workflow, then the complexity of all the workflows has to be down in that choreographed solution versus moving that up to the orchestrator in an orchestrated solution. So there's a direct correlation between how complicated your workflow is and how useful an orchestrator is. Choreography works best for loosely, semantically coupled problems, and be careful trying to fix architecture characteristics problems by changing one dimension. Because if you change that one dimension, it's going to have an unpredictable outcome on the other dimensions that you're dealing with in your architecture. Part of the problem we have here in software architecture is that we're constantly looking for magic silver bullets to solve stuff. And of course, as we all know, there are no silver bullets in software architecture. Instead, it's all about analyzing trade-offs. That's the key skill you need to develop as an architect. So, as I said before, you don't really need to be good at generic architecture. You need to be really good at your specific architecture. Look for tools that you can put in your architect tool belt that are highly specific to your organization that allow you to iterate on design and find the real forces that make a difference versus the advice you read on blogs or conferences or places like that. It's good generic advice, but it doesn't always apply in your scenario. This is why there are no best practices in software architecture. You have to do the trade-off analysis over and over again, which is annoying. It'd be nice if we could solve these problems once and for all and say, always do this communication in microservices, but you can't. But look at it this way. It's great job security for us as software architects because it's got to be done over and over again, and something like ChatGPT is never, well, never is too strong. It's going to be a long time before ChatGPT will give you actual good advice in software architecture. Remember, everything in software architecture is a trade-off. That's it. Thank you very much for coming. Hope you enjoyed it.